All right, the next few examples is how to solve exponential and logarithmic equations as they apply to real-world examples. Okay, so we have the first example called the transparency of a lake. So we have two variables, I sub O and I, and those are the intensity of light before and after going through a material. So I sub 0 is the initial intensity of the light, so it's brighter initially, and then as it passes through a material, it's going to have an intensity I. So I sub 0 is the initial intensity, and I is after it's passed through the material. Okay, X is the distance in feet that light travels in the material, and we have this literal equation here. Okay, negative 1 over K, ln of I divided by I sub 0 equaling X. So K is a new variable in this equation, and K is just some kind of constant. All right, different materials have a different different constant, like water or paper or even like a brick wall. Okay, so K is a constant depending on the type of the material. So question A asks for us to solve this equation for I. So we're not putting any numbers in it whatsoever. We're just going to take the Beer-Lambert law, and I'm going to rewrite it. And we're going to solve this for I. Okay, so right now it's solved for X, which is the distance. Okay, so if we wanted to solve this equation for I, we have a logarithm, okay, a natural logarithm. So in order to solve for I, which is an argument of the natural logarithm, we need to get rid of this coefficient, okay, negative 1 over K. The easiest thing to do here is go ahead and multiply by the reciprocal. That'll cancel this constant out. So if I multiply the left-hand side, I have to multiply the right-hand side by the same reciprocal. So all negative 1's will cancel, the K's will cancel, and I'm left with ln of I divided by I sub 0 on the left-hand side. On the right-hand side, we have xk over negative 1, or I can just write that as negative xk. I'm going to go ahead and bring that negative sign up. Now, to solve for I here, I want to cancel ln. And so in order to cancel ln, we're going to raise both sides by e, because e cancels ln, and I get I divided by I sub 0 equals e to the negative xk. And so since we're solving for I want to multiply both sides by I sub 0. Okay, so I get a final answer here. The I sub 0's will cancel on the left, so I get I equals, we'll go ahead and write the I sub 0 first, e to the negative xk. Right? So we solved this literal equation for a different variable. We started with it equaling the distance in feet, and now it's equal to the intensity of light after it's passed through some sort of material. So on B, we're going to use our answer here to solve. So for a certain lake, okay, the lake has a constant 0.025, okay, and the light intensity starts off I sub 0 at 14 lumens. Find the light intensity at a depth of 20 feet. So I'm actually not sure how these constants work, if this is a fairly clear lake or if it's a murky lake. I'm not really sure. But we can plug the numbers in regardless. So we're going to plug 0.025 for K. We're going to plug 14 in for I sub 0. And we're going to plug in 20 for X because X represents the depth. So I equals I sub 0, which is 14. E to the negative X is 20 feet. And K is the constant 0.025. So all I need to do is plug this into the calculator. Okay, so I'm going to get 14e negative 20 times 0.025 equals 8.49. Right, so I is the intensity of light. The units here that they're using are lumens. So after passing through 20 feet, the intensity of light is almost half, right? Went from 14 lumens to 8.49 lumens. All right, the next word type problems are going to be financial, right? So we're looking at those interest equations. So remember, we have two different interest equations. We have A equals P 1 plus R over N raised to the NT. This is if it's compounded, okay? And then we have the other equation that we use, the PERT equation, if it's compounded continuously. So this is compounded, twice, 4 times, 12 times a year. We would use this one. But if it says compounded continuously, we're going to use the PERT equation. So find the sum of $5,000. A sum of $5,000 is invested at an interest rate of 5% per year. Find the time required for the money to double if the interest is compounded according to the following methods. So if we're compounding this semi-annually, that means n is 2. And so we're going to use this first equation. All right. The interest rate, let's go ahead and figure that out, is 5%. But remember, we want to write that as a decimal. So I'm going to use the interest rate 0.05. P is the principal. The initial amount invested is $5,000. Okay. And the question asks to find the time. So we're not going to plug a number in for T. We're going to solve for T. We want our money to double. So we want the amount of money after we add interest to be $10,000. Okay, so if I plug these numbers in to this equation here, I'll get 10,000 equals 5,000 times 1 plus 0.05 divided by 2 raised to the 2t. Okay. And so I want to solve this equation for t. T is in the exponent, right? So what we want to do is we want to isolate the exponential expression. So the first thing I'm going to do is I'm going to divide by 5,000. So the 5,000s will cancel on the right. 10,000 divided by 5,000 is 2. I'm going to go ahead and simplify the parentheses in here. Half of 0.05 is 0.025, and so I'm going to get 1.025 raised to the 2t. Okay, so we're really getting 2.5% interest, okay, every 6 months. So now solving this for t, the t is in the exponent, and I can't solve things if t is in the exponent. I need to bring this down to the main line. And the way we do that is we ln, right? So we're going to ln both sides. Now ln is not going to cancel 1.025, right? So these don't cancel, but the 2t can come out in front of this natural logarithm. So we're going to get ln of 2 equals 2t times ln of 1.025, right? Bring those exponents down before you solve for them. Now, to solve this for t is being multiplied times 2, and it's being multiplied by ln of 1.025. So I'm just going to divide by 2 ln of 1.025 on both sides. Right? And that is going to, on the right-hand side, it's going to cancel both the 2 and the ln and leave us just with t. So if I plug this into the calculator, I will have the time it takes for this money to double. So in the calculator, I'm going to type in ln of 2, close those parentheses, divided by. Now, because the denominator here has 2 times ln of 1.025, I'm going to put it in parentheses. 2 times ln 1.025 close the parentheses for the ln, close the parentheses for the denominator, and I get 14.0355, right? So I'm just going to round that to about 14. Now 14 what? Right? This is a time interval, and our time is in years, okay? So it's going to take 14 years for this money to double from 5,000 to 10,000. Now, question B says, how long will it take if the money is compounded continuously? So if we have a continuous interest being added to our account, is that going to, surely it's going to shorten the amount of time that it's going to double. But if it's compounded continuously, we're going to use the PERT equation. And so I'm going to get the amount is still 10,000 because we want the money to double. The principal is the initial investment, e to the 0.05t. Okay, so I'm using the same numbers. I'm just replacing the n with e. Okay, so here I have an equation, and I need to solve for t, and it's inside this exponential expression. The exponential expression is just e to the 0.05t, so I want to get rid of this constant. So the first thing I'm going to do again is divide by 5,000. It'll cancel on the right, and then I'm going to get 2 on the left. And in order to solve for t in the exponent, I need to bring it down. So I'm going to ln this again. But since the exponential base is e, ln and e will cancel. So I get 0.05t on the right and ln of 2 on the left. And so to solve for t, I just need to divide by 0.05. So I get t equals, and I'm going to plug that into the calculator, ln of 2 divided by 0.05. ln 2 divided by 0.05 gets me 13.86. So it actually didn't really shorten the number of years too much. Okay, it went from 14 years to 13.86, and that's usually true. Okay, if you have the choice between compounding your interest more frequently or raising the interest rate is going to give you the biggest return. All right, so keep that in mind. Higher interest rate is always better when you're investing. Lower interest rate is always better when you're taking out a loan. Okay, so interest rate makes more difference than the number of times it's compounded. All right, so last problem here. The time required to grow an investment. So we have a sum of 1,000 this time. Interest rate is 4% per year. Find the time required for the amount to grow to 4,000 if the interest is compounded continuously. So this frequency of compounding the interest tells us that we need to use the PERT equation. Okay, A equals P raised to the RT. So the amount, we want to grow 1,000 to 4,000. So the amount is 4,000 after interest. 1,000 is our principal. The interest rate, 4% written as a decimal, 0.04. And then the time, the t value, that's what we're looking for. So I have this equation, 4,000 equals 1,000 e to the 0.04t. So the exponential part is just the e to the 0.04t. So I need to get rid of this constant. So the first thing I'm going to do is divide by 1,000. 4,000 divided by 1,000 is 4. And then I have e to the 0.04t. So I have an exponential equation here. I want to solve for t. So I need to bring this down, okay, or cancel the base. So ln, we'll do both of those, right? So on the left-hand side, I have ln of 4. On the right-hand side, ln and e will cancel, and I have 0.04t here. So solving for t, I'm going to divide by 0.04 and plug that into the calculator, right? ln of 4 divided by 0.04 gets me 34.65. 34.65 what? Okay, our interest rate is in years, so this is how many years it would take the money to basically quadruple. Okay, 35 years. All right, so that completes section 4.5.